Force sample problem number 3. This is a Newton's third law problem. As you recall, Newton's third law states that every action has an equal and opposite reaction. The idea behind this is that when two objects interact with each other, they apply a force equivalent to the ones acting on each other, but on the opposite object. So for example, if object A hits object B to the right, object B hits back with the same force, but to the left. So they're action-reaction forces, but they happen on different objects. So here in this example, we have two students, and they're both standing on ice with extremely low friction shoes. The idea behind this is with low friction shoes, we can ignore the forces of friction. Of course, that's not ideal. In a real-world situation, friction would matter, but we are still just learning the basic ideas. So when you see this expression, extremely low friction, that implies that you can ignore the force of friction in these particular cases. So student Amy, or student A, has a mass of 60 kilograms, and student Balja, or student B, has a mass of 80 kilograms, clearly all muscle. Now, Amy pushes Balja. So this is the force of Amy acting on Balja, and it is with a force of 20 newtons to the right. And she applies this force for 2 seconds. So Balja is experiencing a force of 20 newtons to the right. But according to Newton's third law, Balja will be producing an equal but opposite force on Amy towards the left. So part A, we need to draw a free body diagram of both the students. Part B, we're trying to determine Balja's acceleration as a vector. Part C, Amy's acceleration as a vector. Part D, we're trying to find Balja's final velocity. And part E, we're looking for Amy's final velocity after the push. When doing the givens, recording the information, we have to use the appropriate third law notation. In addition, we have to get the subscripts, I should say, correctly. So M subscript A is the mass of Amy, or which I'll just refer to as student A, 60 kilograms. And M subscript B stands for Balja's mass, which I will just refer to as student B, of 80 kilograms. Based on this, student A's mass is lower than student B, which we would expect then that student A should accelerate at a greater rate than student B because of Newton's second law. And that is the rate of acceleration is directly related to the force applied, but indirectly related to its mass. And this key notation, FA on B. So this is the force of Amy on Balja, or student A on student B, and that is 20 newtons to the right. And the time for this push is 2 seconds. Now notice I didn't bother putting a subscript on time, and the reason being, I should say, is that the time of 2 seconds applies to both students. So for part A, you're looking for the free body diagram of student A and student B. You're looking, in part B, you're looking for the acceleration of student B. Part C, the acceleration of student A. Part D, the final velocity of student B. And part E, the final velocity of student A. The key to drawing the free body diagrams is being disciplined with using the appropriate subscripts on each diagram here. This is how this reads. We know that Amy was pushing Balja to the right. So let's focus on the FBD of Balja, or student B. Student B is being pushed to the right, and this is the force of A acting on B. This here is that 20 newtons to the right. And if you notice, all of the subscripts are in reference to student B. So this is the normal force acting on B. This is the mass of B, the force of gravity of B, and the force of A on B. It's always with respect to student B. Now, when we take a look at student A, Amy in this case, the key here is this is the reaction force from Balja, or student B, if you will, FB on A. And it's going to be equal, but in the opposite direction. This implies this will be a force of 20 newtons, but in the negative direction. And again, look at the subscripts. Subscript A, FB on A. Those are key. Part B, we're looking for the acceleration of student B. So since we're looking for the acceleration of student B, we're referring to free body diagram B only. Now, when you look at the net force equation, F net B is equal to FA on B plus the normal force acting on B plus the weight acting on B. These three vectors are not collinear, but the good news is the relationship between the normal and the weight. Since they are not floating or sinking, therefore F net Y equals 0 newtons because we have two components, the x component and the y component. But the good news again, since the y component cancels out, we don't have to do any special component method to solve this problem because of this convenience right here. So on the next line, notice I've replaced the harpoon with positive, and that's because that force is acting to the right. But this line here comes from Newton's second law, and that is F net equals ma. So since we're talking about F net acting on B, we have to have the B subscripts. Isolating for AB, we remove MB by division. And again, this is because MB is attached to AB through multiplication. And the opposite of multiplication, of course, is division. Substituting our values in, we get an acceleration of positive 0.25 meters per second squared, or 0.025, let's try that again, 0.2500, there we go, meters per second squared. And apparently I am forgetting about my sig figs as well. And positive turns into right in this case. Part C. Now we're looking for the acceleration of Amy, or student A. In this particular case, we more or less have the same equation as we had with student B, but the directions are different. So F net A is equal to FB on A plus Fn A plus FGA. And again, if we look at the free body diagram of Amy, we have vectors in the x component and vectors in the y component. In normal circumstances, we'd have to use component method and solve it with a more in-depth procedure. However, the good news is that our y components cancel out, so they don't actually contribute to the overall net force. So once again, the normal and the weight cancel each other out because it is not floating or sinking. Therefore, the y component is 0 newtons. Dropping vector notation and substituting in some formulas, we know that F net is equal to ma, that's Newton's second law. So F net A is equal to ma times the acceleration of A, which is equal to negative FB on A. Now the negative implies to the left, but we need that value. And this is how you actually show the proof. Now I did mention that we knew that it's going to be equal and opposite, but for communication purposes and how to justify this, this is the standard solution. So we're trying to find FB on A. And there, I put my harpoon up there, make it a little bit better. And to argue it, you need the following three lines. Since FB on A is equal to negative FA on B, and this literally reads, every action has an equal but opposite reaction. That's the third law. So that's translating it into the language. And of course, when you write this statement, you must also include this, Newton's third law, to justify the statement. So this is your first argument. So your first argument is every action has an equal but opposite reaction. And your second argument is this. And we know that the force of A on B is 20 newtons to the right. Based on this, therefore, we can conclude that the force of B on A is going to be 20 newtons, but to the left. And that is all you need to write to prove, so to speak, the relationship between FB on A and FA on B. And again, the left is why we have the negative here. Isolating for acceleration of student A, of Amy, we have to remove MA. MA is attached through multiplication. The opposite of multiplication, of course, is division. So we get negative 20 over 60, which gives us negative 1/3 meters per second squared, or 0.3333 meters per second squared to 4 sig figs. Of course, this fractional way of expressing it is more robust, and it's to the left. And to point out one observation, since Amy has less mass, Amy's acceleration should be greater than that of Bulja. And it is. And finally, for parts D and part E, we're looking for the final velocity of both student B and student A. This is a kinematics thing. And again, what relates kinematics and dynamics is acceleration. So to determine the appropriate formula, essentially you make the list of kinematic formulas relevant. So we have dB, VB1, VB2, acceleration B, time B. So the time was given of 2 seconds, and we know they both start from rest. So the VB1 was 0 meters per second. And the third thing we need, obviously, is one of the remaining kinematic parameters, either dB or the acceleration. And we have found the acceleration to be 0.25. So we have 2 green givens and 1 amber. Hence, and of course, we're not working with dB, VB2 is equal to VB1 plus ABTB. And we use the same formula for student A because we have the same type of information. So substituting in, positive 0.25 times 2 is 0.5 meters per second. Therefore, VB2 is 0.5 meters per second to the right, except 0.5000 meters per second to the right. And finally, finding VA2. And I noticed I forgot to put my harpoons up there, so just fix that. So substituting that in, we know that Amy also starts from rest. Her acceleration is negative because it is to the left, 1/3, and the time is 2 seconds. So we get negative 2/3 meters per second, or negative 0.6667 meters per second. But since we have a nice fraction here, we can express our final velocity, VA2, as 2/3 meters per second to the left.